Every single night, 7.9 billion people fall asleep beneath the same ancient guardian, a sphere of rock and dust, 3,474 kilometers wide, locked in an eternal embrace with Earth at precisely 384,400 kilometers away. It holds 73 billion trillion kilograms of mass, enough gravity to lift entire oceans twice every single day. Without it, scientists calculate our planet would spin so wildly that summers could reach 80 degrees Celsius and winters could freeze the equator solid. Now imagine something strikes it, something massive, something fast. A crack appears, silently, slowly. Then, all at once, the moon splits in half. Within hours, debris the size of cities begins falling toward Earth. Within days, our tides become 100-meter walls of chaos. Within months, the sky itself turns against us. NASA has calculated that cracking the moon would require more energy than 2 quadrillion nuclear bombs detonating at once. They assumed it was impossible, but the universe does not care what we assume. Tonight, we ask a question that should terrify you. What happens to our planet, our oceans, our climate, and every living thing on Earth when we lose the one companion that has protected us for 4.5 billion years? The answer will change how you look at the night sky forever. Prepare for a journey through cosmic catastrophe beyond comprehension. We begin. Look up tonight, and you will see it. A pale circle of light hanging in the darkness. It has been there since before you were born. It was there when your great-grandparents walked this earth. It watched the dinosaurs roam and the first fish crawl onto land. For 4.5 billion years, the moon has been Earth's closest companion. Silent, patient, eternal. We rarely think about it. The moon is simply there, like the air we breathe or the ground we stand upon. It rises, it sets, it changes shape from a thin sliver to a glowing disk and back again. We use it to mark our months. Lovers gaze at it, poets write about it, but most nights we forget it exists at all. This is a mistake, because the moon is not just a pretty light in the sky, it is the reason you are alive. Let me explain. The moon sits roughly 384,400 kilometers away from Earth. That sounds far, but in space terms, it is remarkably close. If Earth were a basketball, the moon would be a tennis ball placed about 7 meters away, close enough to touch in the grand scale of the cosmos. And this closeness matters more than you might imagine. Every moment of every day, the moon pulls on our planet. Its gravity reaches across the void and grabs hold of Earth's oceans. This is why we have tides. When the moon passes overhead, it tugs the water toward itself, creating a bulge. This bulge travels around the planet as Earth rotates, giving us high tides and low tides, 2 high tides and 2 low tides every single day, like clockwork. Without the moon, our tides would be weak and small. They would be controlled only by the distant sun. But with the moon, our tides are strong. They are powerful enough to shape coastlines over millions of years. They are powerful enough to drive ocean currents that carry heat around the globe. They are even powerful enough to slow down Earth's rotation, bit by bit, century by century. 4 billion years ago, a day on Earth lasted only 6 hours. The moon's gravity has been acting like a gentle brake, gradually slowing us down to our current 24-hour day. But the moon does something even more important. It keeps Earth stable. Imagine a spinning top. When it spins fast and true, it stands upright. But when it starts to wobble, it becomes unpredictable. It tilts wildly. It may even fall. Earth is like that spinning top. It rotates on an axis tilted at 23.5 degrees. This tilt gives us our seasons. When the northern hemisphere leans toward the sun, we get summer. When it leans away, we get winter. This gentle, predictable cycle has allowed life to flourish for billions of years. But here is the strange truth. Without the moon, Earth's tilt would not stay at 23.5 degrees. It would wander. Scientists have run simulations, and the results are disturbing. Without lunar gravity holding us steady, Earth's axial tilt could swing between 0 and 85 degrees over millions of years. 0 degrees means no seasons at all. 85 degrees means the poles would point almost directly at the sun. Imagine 6 months of endless daylight at the equator, followed by 6 months of total darkness. Temperatures would swing by hundreds of degrees. Ice ages would come and go with terrifying speed. Life as we know it could never have evolved. The moon is our stabilizer, our anchor, the silent hand that keeps our world from going mad. And there is more. Some scientists believe the moon played a role in the very origin of life on Earth. This is still debated, and not everyone agrees. But the theory goes like this. In the early days of our planet, the moon was much closer than it is now. The tides it created were enormous. Imagine walls of water rising and falling hundreds of meters every few hours. These extreme tides could have concentrated the chemicals needed for life in shallow pools along ancient shorelines. As the water rose and fell, these chemicals mixed again and again, creating the conditions for the first simple cells to emerge. We cannot prove this yet. We may never prove it. But the possibility haunts every scientist who studies the origin of life. The moon may not just be our companion, it may be our creator. There is also a stranger idea, one that lives on the fringes of science. Some researchers have wondered if the moon is too perfect, too round, too precisely placed, the exact size needed to perfectly eclipse the sun during solar eclipses, the exact distance needed to stabilize our axis, the exact mass needed to generate our tides. Is this luck? Is this coincidence? Or is there something we do not understand? Most scientists dismiss this as pattern seeking in random data. The moon is what it is because of physics, not design. But the question lingers in the darker corners of our imagination. Now, let us pause. Let us stand beneath this ancient guardian and ask a question that should never be asked. What if something cracked the moon in half? Not a small crack. Not a surface fracture. A true splitting. A catastrophic rupture that tears through billions of tons of rock and iron and dust. What force could do such a thing? What would happen in the seconds, minutes, days, and years after such an event? What would become of our tides, our seasons, our climate, our sky, our very survival? This is not a question for the faint of heart. The answers are terrifying. They challenge everything we take for granted about our place in the universe. They force us to confront how fragile our existence truly is, but we are going to ask anyway. Because sometimes the only way to understand what we have is to imagine losing it. Sometimes the only way to appreciate the light is to stare into the darkness. The moon has protected us for billions of years. Tonight, we will imagine a universe where that protection ends. We will walk through the fire and ash of a broken sky. We will witness oceans rise and fall without purpose. We will feel the ground shake beneath bombardments of lunar stone. And perhaps, by the end, we will look up at that silver disk with new eyes, with gratitude, with wonder. But first, we must understand the force required to shatter a world. The moon looks so peaceful from Earth, a gentle glow in the night sky, a soft companion that never threatens, never changes, never frightens. But appearances lie. The moon is not a fragile ornament. It is a fortress of stone and iron, forged in the violence of the early solar system. To crack it in half would require a force beyond anything humanity has ever created, beyond anything we can truly imagine. Let us begin with size. The moon measures 3,474 kilometers across. That is roughly the distance from Los Angeles to New York City. If you could drive across the moon at highway speeds without stopping, it would take you about 35 hours. But you cannot drive across the moon. There are no roads. There is no air. There is only rock, dust, and silence stretching in every direction. The moon weighs approximately 73 billion trillion kilograms. Written out, that number looks like this: 73 trillion kilograms. Your brain cannot truly grasp this number. Nobody's brain can. So, let us try a different approach. Imagine every car ever built in human history. Every truck, every airplane, every ship, every building, every bridge, every statue. Now imagine piling all of that onto a scale. The moon would still weigh millions of times more. It is a mountain of mountains, a world unto itself. And here is what makes it even harder to break. The moon is held together not just by the strength of its rock, but by its own gravity. Every piece of the moon pulls on every other piece. The surface pulls on the core. The core pulls on the surface. This mutual attraction creates what scientists call gravitational binding energy. It is the energy you would need to overcome to completely scatter the moon into pieces drifting through space. The gravitational binding energy of the moon is staggering. Scientists calculate it at roughly 1.2 times 10 to the power of 29 joules. Again, this number means nothing to the human mind. So, let us compare it to something we know. The atomic bomb dropped on Hiroshima released about 63 trillion joules of energy. To match the moon's gravitational binding energy, you would need to detonate approximately 2 quadrillion Hiroshima bombs, all at once, in the same place. Humanity's entire nuclear arsenal, every warhead ever built, represents less than a speck of dust compared to this requirement. But wait, we are not trying to completely destroy the moon. We are only trying to crack it in half. Surely that requires less energy. Yes, but not by as much as you might hope. To split the moon along a clean fracture would still demand something in the range of 10 to the power of 27 joules. This is still equivalent to billions of nuclear weapons detonating simultaneously at the moon's core. Still impossible for human technology. So, what in the universe could deliver such a blow? The first candidate is an asteroid. Space rocks strike the moon constantly. Look at its surface through a telescope, and you will see the evidence everywhere. Craters upon craters upon craters. The moon is a scarred warrior, marked by 4 billion years of bombardment. Some of these impacts were enormous. The South Pole Aitken Basin, on the far side of the moon, stretches 2,500 kilometers wide and plunges 8 kilometers deep. The asteroid that created it was probably around 170 kilometers across. It struck with the energy of billions of nuclear bombs. Yet the moon survived. Wounded, yes. Reshaped, certainly. But not cracked, not split. The blow was absorbed by the sheer mass of lunar rock. The crater formed, the debris flew, and the moon remained whole. To crack the moon in half, you would need something far larger, something moving far faster. Scientists estimate that an object at least 300 to 500 kilometers in diameter, traveling at speeds exceeding 20 kilometers per second, might begin to approach the necessary energy. This is not an asteroid. This is a dwarf planet. Think of something the size of Vesta, one of the largest objects in the asteroid belt. Now imagine it screaming toward the moon at 70,000 kilometers per hour. The impact would not be a collision. It would be an apocalypse. But even this might not cleanly crack the moon. More likely, it would shatter both objects into countless fragments, creating a ring of debris around Earth. The moon would not split like a broken plate. It would explode like a water balloon struck by a bullet. The physics of hypervelocity impacts is strange and violent. At such speeds, rock behaves more like liquid than solid. Shock waves travel through the material faster than the material can respond. There is another candidate, more terrifying still. A rogue planet. Our solar system is relatively stable now. The planets orbit in predictable paths. But the universe is full of wanderers. Planets ejected from their home systems, drifting alone through the darkness between stars. Some scientists estimate there may be billions of rogue planets in our galaxy alone. Most will never come near Earth. The distances between stars are too vast, the chances too slim. But what if one did? A rogue planet the size of Mars, passing through our inner solar system, would create gravitational chaos. It would not need to strike the moon directly. Its gravity alone could tear the moon apart through the tidal forces. Imagine the moon stretched like taffy as the rogue planet passed by. One side pulled toward the intruder, the other side pulled toward Earth. The stress would build until the rock itself could take no more. This is how some moons in our solar system may have died. Jupiter's immense gravity is thought to have destroyed ancient moons, it grinding them into the faint rings that circle the giant planet today. Saturn's rings may contain the frozen remains of a moon that wandered too close. The universe is not kind to small bodies that stray into dangerous territory. There is one more possibility, stranger than the rest. Some physicists have imagined what would happen if a small black hole passed through the moon. Not a supermassive black hole, but a primordial one, perhaps the mass of a mountain compressed into a space smaller than an atom. Such an object would punch through the moon like a bullet through paper. The tunnel it left behind would destabilize the entire structure. We have never observed a primordial black hole. We do not know if they exist, but the mathematics allows for their existence, and scientists continue to search. The truth is sobering. Nothing in our solar system, as it exists today, is likely to crack the moon in half. The age of heavy bombardment ended billions of years ago. The great impactors have been swept up. The rogue planets remain distant strangers, but the universe is old, and patience is its greatest weapon. What seems impossible today may simply be waiting for tomorrow. Let us now imagine that tomorrow has arrived. Something, somehow, has delivered the killing blow. The force has been unleashed. In the next heartbeat, the moon begins to break. The blow has landed. After billions of years of patient survival, the moon has met its match. In the vacuum of space, there is no sound, no thunderclap, no roar of destruction, only silence as ancient rock begins to tear itself apart. Let us slow down time. Let us witness this moment frame by frame, second by second, because what happens next will unfold faster than human eyes can follow. In real time, the entire process would take mere minutes, but within those minutes, a world ends. The impactor strikes the lunar surface at impossible speed, perhaps 20 kilometers per second, perhaps faster. At this velocity, the object does not push into the moon. It does not dig a crater in the normal sense. Instead, it transfers its energy so quickly that the rock beneath it cannot move out of the way. The rock has no time to crack, and no time to crumble. It simply vaporizes. In the first millisecond, a flash of light brighter than the sun erupts from the impact site. If you were watching from Earth, this flash would be visible even in daylight. A new star appearing on the face of the moon, burning for just an instant before fading. The temperature at the impact point exceeds 10,000 degrees. Rock becomes gas, gas becomes plasma. A bubble of superheated matter expands outward at thousands of meters per second. But the flash is only the beginning. Beneath the surface, something far more violent is happening. A shock wave is born. This is not like a wave in water, gentle and rolling. This is a wall of compressed energy, slamming through solid rock at 5 kilometers per second. Imagine a tsunami made of stone, invisible and unstoppable, irradiating outward from the wound in all directions. The moon's structure, so carefully built over billions of years, now becomes its enemy. Let us look at what lies beneath the dusty grey surface. The outermost layer is the crust, roughly 50 kilometers thick on the near side and over 100 kilometers thick on the far side. This crust is made of ancient rock called anorthosite, pale and rigid, formed when the moon was young and molten. Below the crust lies the mantle, a thick shell of denser rock extending nearly 1,000 kilometers deep. And at the very center sits the core, a small ball of iron and nickel, perhaps 350 kilometers across. Some scientists believe parts of this core remain liquid, even today, slowly cooling over the eons. The shockwave cares nothing for these layers. It tears through crust, mantle, and core without slowing. But as it travels, it does something terrible. It fractures everything it touches. Rock is strong, but it is also brittle. Think of a ceramic plate. It can hold great weight when the force is applied evenly. But strike it with a hammer, and it shatters instantly. The moon is like that plate. For billions of years, gravity has held it together, pressing evenly from all sides. But now, a hammer has fallen. Cracks begin to form. Not small surface fractures, but deep wounds that reach toward the core. These cracks propagate at nearly the speed of sound in rock, roughly 5 kilometers per second. Within 10 seconds, fractures have traveled 50 kilometers deep. Within a minute, they have crossed hundreds of kilometers. The moon is breaking from the inside out. Here is something strange that scientists still debate. When an object this large begins to fracture, does it break cleanly or chaotically? Some models suggest that a moon-sized body would split along predictable planes, like a crystal cleaving along its natural structure. Other models suggest the opposite, that the fractures would branch and multiply, creating countless fragments of random sizes. We have never witnessed such an event. We can only guess based on mathematics and computer simulations. What we do know is that gravity will not release its grip easily. Even as the moon cracks, its own gravitational pull fights to hold the pieces together. This creates a strange, slow-motion ballet of destruction. The two halves do not fly apart like shrapnel from a bomb. Instead, they begin to drift, slowly at first, or just centimeters per second. The gravitational bond between them remains strong, even as the physical bond shatters. But momentum is a patient force. The energy of the impact has been transferred into the lunar fragments. They are moving, and they will not stop. Over hours and days, the gap between the two halves widens. What was once a single world becomes two broken pieces, tumbling through space. And they do not tumble alone. Between the two halves, a cloud of debris is forming. Smaller fragments, ranging from dust particles to boulders the size of houses, fill the space where the moon used to be. This debris cloud glows faintly, still hot from the energy of the impact. Some pieces collide with each other, shattering further. Others escape entirely, flung outward by the violence of the rupture. From Earth, yet the sight would be unlike anything in human history. The familiar round moon would be gone. In its place, two dark shapes would drift apart, surrounded by a glittering haze of destruction. At first, you might not believe your eyes. You might think it was a trick of the light, a strange cloud passing in front of the moon. But as the hours passed, the truth would become undeniable. The moon is broken. There is a haunting detail that few consider. The moon has been struck by countless asteroids over its lifetime. Each impact left a crater. Many of these craters contain water ice, trapped in permanently shadowed regions near the poles. When the moon cracks, this ice would be exposed to sunlight for the first time in billions of years. It would sublimate instantly, turning from solid to gas without passing through liquid. A faint mist of ancient water would drift into space, a ghost of the moon's hidden reserves escaping into the void. Some researchers believe there may be more water ice on the moon than we currently estimate. Hidden in deep caves called lava tubes, protected from the harsh surface conditions. If the moon cracked along the right plane, these caves would be torn open. Their secrets would spill into the vacuum. We would learn more about the moon's interior in one catastrophic moment than in decades of careful exploration. But there would be no one left to celebrate this knowledge. Because now, the debris is beginning to move, not just drifting aimlessly, but falling toward the largest source of gravity in the neighborhood, Earth. Our planet sits below, blue and green and utterly unaware of what is coming. The first fragments are small, no larger than grains of sand. They enter the atmosphere as shooting stars, burning up harmlessly. But behind them come larger pieces, and behind those, larger still. The sky is about to change forever. For as long as humans have existed, the night sky has been a place of comfort. We have named the stars. We have traced patterns in their arrangement. We have used them to navigate oceans and predict seasons. The sky has been our constant, our calendar, our companion. But tonight, the sky is wounded. Where the moon once hung, a new shape is forming. Not a circle, not a crescent. Something broken, something wrong. Two massive fragments drift apart like the halves of a shattered egg. Between them, a cloud of debris spreads outward, catching the sunlight and scattering it in strange directions. The familiar silver glow is gone. In its place, a glittering smear stretches across the darkness. From Earth, this transformation would unfold over hours and days. At first, you might notice that the moon looks slightly different, and perhaps a dark line across its face, perhaps an unusual brightness at its edges. You might think your eyes are tired. You might blame the atmosphere, the weather, the angle of your vision. But as time passes, the truth becomes impossible to ignore. The moon is no longer one object, it is many. Let us examine what fills the sky now. The two primary halves of the moon still contain most of the original mass. Each half weighs roughly 36 billion trillion kilograms. They are still enormous, still world-sized, but they are no longer spherical. Gravity has not yet had time to reshape them. They tumble awkwardly, their broken edges catching light and casting strange shadows. Between these two giants floats the debris field. This is not a thin scattering of dust. This is a dense cloud of material, stretching thousands of kilometers in every direction. The pieces range from microscopic particles to chunks the size of mountains. Some spin rapidly, glinting like diamonds. Others drift slowly, dark and silent, absorbing light rather than reflecting it. Scientists have studied what happens when celestial bodies break apart. We have observed asteroid collisions. We have watched comets fragment as they approach the Sun. From these observations, we can predict the behavior of lunar debris. The smallest particles, those less than a millimeter across, would spread the fastest. They would form a hazy glow around the Moon's former position, a ghostly ring that circles Earth. Over weeks and months, this ring would thin and spread, eventually becoming invisible to the naked eye. But it would not disappear. These particles would remain in orbit for years, perhaps decades, slowly raining down into our atmosphere as a constant shower of microscopic meteors. The medium-sized fragments, those ranging from pebbles to boulders, would behave differently. Some would settle into stable orbits around Earth. Others would collide with each other, shattering further. Still, others would be flung outward by the chaos of gravitational interactions, escaping into orbits around the Sun. Earth might capture a few small moons from this debris, temporary companions that circle our planet for centuries before eventually falling or escaping. The largest fragments pose the greatest concern. Anything larger than a few hundred meters could survive passage through Earth's atmosphere and strike the surface with devastating force. And the debris cloud contains countless objects of this size. But we will speak of impacts later. For now, let us simply observe the sky. Imagine standing outside on the first night after the rupture. The sun has set, the stars emerge one by one, and where the moon should be, you see something that makes your heart stop. A streak of light stretches across a quarter of the sky. Not a meteor, not a comet, something far larger. The debris cloud catches the last rays of sunlight, glowing with an eerie luminescence. Within this glow, you can make out darker shapes. The two halves of the moon, still recognizable, still massive, but now separated by a visible gap. They look wounded. They look wrong. This sight would trigger panic across the world. Religions would struggle to interpret the sign. Scientists would rush to their telescopes. Governments would hold emergency meetings. Social media would explode with theories, fears, and prayers. For the first time in history, every human on Earth would share the same terrifying view, and the sky would only grow stranger. As days pass, the debris field would evolve. The pieces would not stay in a neat cloud. They would spread, stretch, and disperse. Some would form temporary rings around Earth, similar to the rings of Saturn, but far messier. These rings would not be beautiful. They would be chaotic, uneven, constantly shifting as fragments collided and scattered. Here is a detail that few would consider in the initial panic. The debris field would affect our ability to see the stars. For all of human history, we have looked through clear space to observe the universe. Our telescopes have captured light from galaxies billions of light years away. We have photographed black holes, mapped cosmic background radiation, and tracked asteroids that might threaten our planet. This work depends on a clear line of sight between Earth and the cosmos. The lunar debris field would create a haze, not thick enough to block our view entirely, but enough to scatter and distort incoming light. Ground-based astronomy would suffer. Space telescopes would need to navigate through clouds of debris, risking collisions with every orbit. The Hubble Space Telescope, the James Webb Space Telescope, and countless satellites would face a new and deadly hazard. Some scientists have speculated about an even stranger possibility. If enough debris settles into stable orbits around Earth, it could form a permanent ring system. Earth would join Saturn, Jupiter, Uranus, and Neptune as a ringed planet. This ring would not be made of ice like Saturn's famous bands. It would be made of rock and dust, the shattered remains of our former moon. From the surface, this ring would be visible as a bright arc across the night sky. It would never set, never move, always hanging in the same position relative to the equator. Future generations, if any survived, might grow up thinking this was normal. They might never know that Earth once had a single, round, beautiful moon. But that future is far away. Right now, the sky is falling. The first fragments are beginning their long descent toward Earth. Most are small. They burn up in the atmosphere, creating spectacular meteor showers that light up the night with streaks of fire. For a few nights, and it might almost seem beautiful, a light show to accompany the apocalypse. But the larger fragments are coming. They fall more slowly, pulled by gravity, heated by friction. They glow red, then orange, then white. They do not burn up. They survive. And when they land, everything changes. Before the first fragments strike Earth, something else begins to go wrong. Something invisible. Something that touches every coastline on the planet within hours of the rupture. The tides are dying. For billions of years, the moon has pulled on Earth's oceans with steady, predictable force. High tide, low tide, high tide, low tide. Twice each day, the waters rise and fall like the breathing of a living planet. Fishermen know these rhythms. Sailors depend on them. Entire ecosystems have evolved around the daily dance of water and shore. Now that dance is ending. When the moon cracked in half, its gravitational influence did not vanish, but it changed dramatically. Instead of one large mass pulling from one direction, there are now two smaller masses pulling from different directions, and between them, a chaotic cloud of debris exerts its own tiny tugs in countless directions. The result is gravitational confusion. Imagine you are floating in a swimming pool. Someone stands at one end and creates waves by pushing the water rhythmically. The waves are predictable. You can time them. You can prepare for them. Now imagine 10 people standing around the pool, all pushing the water at different times, in different directions, with different strengths. The waves become chaos. They crash into each other. They cancel out in some places and amplify in others. The water becomes impossible to predict. This is what happens to Earth's oceans. In the first hours after the rupture, coastal communities would notice something strange. The tide tables, carefully calculated years in advance, would suddenly be wrong. A high tide might arrive 2 hours late, or 3 hours early, or not at all. A low tide might expose seafloors that have never seen daylight, or a surge might flood areas that have always been safe. Scientists at oceanographic institutes around the world would scramble to understand what is happening. Their computer models, designed for a single moon, would produce nonsense when fed the new gravitational data. They would need weeks, perhaps months, to develop new models. But the oceans would not wait. Here is a scientific fact that most people do not appreciate. The moon does not just create two high tides on opposite sides of Earth. It creates a complex pattern of water movement that circulates around the entire planet. This pattern is called the tidal current system, and it is connected to everything. Tidal currents carry warm water from the equator toward the poles. They carry cold water from the poles toward the equator. They distribute nutrients that feed ocean ecosystems. They influence weather patterns. They even affect the rate at which heat escapes from Earth's interior through underwater volcanic vents. With the moon broken, these currents would falter. The immediate effects would be felt in coastal ecosystems. Tide pools, those small pockets of water left behind when tides recede, are home to countless species of fish, crabs, snails, and seaweed. These creatures have evolved to survive the daily cycle of submersion and exposure. They can handle being underwater. They can handle being in open air. But they cannot handle randomness. If the tides become unpredictable, tide pool creatures would die in massive numbers. Some pools would dry out completely, baking their inhabitants in the sun. Others would remain flooded for days, depriving air-breathing species of oxygen. The delicate balance that has sustained these ecosystems for millions of years would collapse within weeks. Coral reefs would suffer next. Many coral species spawn according to tidal cycles, releasing eggs and sperm during specific tidal conditions. If those conditions become random, coral reproduction would fail. Reefs already stressed by warming oceans and acidification would face a new and unexpected threat, but the chaos would not stay in the water. Coastal cities around the world would face a new and terrifying reality. Storm surge predictions, which save thousands of lives every year, depend on accurate tide forecasts. When a hurricane approaches, emergency managers calculate how high the water will rise based on the storm's strength and the current tidal conditions. They know that a hurricane arriving at high tide is far more dangerous than one arriving at low tide. With unpredictable tides, these calculations become impossible. A hurricane might strike when the ocean is mysteriously higher than expected, flooding neighborhoods that should have been safe. Or it might arrive during an unexpected low, sparing areas that had been evacuated. Emergency planning would become guesswork. Thousands would die from errors that were not really errors at all, just the universe refusing to follow the old rules. There is a stranger consequence that scientists have only recently begun to understand. The tides affect earthquakes. This sounds surprising, but the evidence is solid. The weight of ocean water pressing down on tectonic plates varies with the tides. During high tide, more weight pushes down. During low tide, less weight pushes down. This rhythmic pressing and releasing can trigger earthquakes in faults that are already under stress. Not large earthquakes, usually, but small ones. The moon, through the tides, has been gently massaging Earth's crust for billions of years. With chaotic tides, this massaging would become unpredictable. Some faults might experience unusual stress patterns. Others might be relieved of pressure in unexpected ways. The overall effect on earthquake frequency is unknown. No one has ever studied a planet with a broken moon. But some scientists speculate that seismic activity could increase in the months and years following the rupture. And then there are the megatides, where here is something terrifying to consider. When the two halves of the moon align with Earth and the Sun, their combined gravitational pull would create tides far larger than anything in human experience. Not twice the normal height, perhaps 10 times, perhaps more. Imagine a wall of water, 30 meters high, surging up the Thames River into London. Imagine Tokyo Bay emptying completely, then refilling with catastrophic speed. Imagine the entire coastline of Bangladesh, home to over 150 million people, submerged under an unstoppable flood. These megatides would not happen every day. They would depend on the positions of the lunar fragments, but they would happen. And when they did, no seawall would hold. No evacuation would be fast enough. Humanity built its greatest cities along coastlines. New York, Shanghai, Mumbai, Los Angeles, Sydney, Lagos. We built them there because the sea provided food, trade, and transportation. We trusted the ocean to behave. That trust is now broken, like the moon itself. And while the waters rage, another disaster is beginning. Far above, in the mechanics of planetary motion, Earth's axis is starting to wander. High above the churning oceans, something invisible is shifting. You cannot see it. You cannot feel it. But it will change everything about life on Earth. The planet's axis, that imaginary line around which our world spins, is beginning to drift. For billions of years, the Moon has acted like a gyroscope for Earth. It has kept our axial tilt steady at approximately 23.5 degrees. This tilt is why we have seasons. When the northern hemisphere leans toward the sun, summer arrives. When it leans away, winter comes. Spring and fall mark the transitions between these extremes. This predictable cycle has shaped every aspect of life on our planet. Plants bloom in spring because they know warmth is coming. Animals migrate in fall because they know cold is approaching. Farmers plant and harvest according to ancient calendars built around these reliable patterns. Human civilization itself was constructed on the foundation of seasonal predictability. Now that foundation is crumbling. Without the Moon's stabilizing gravity, Earth becomes like a spinning top that has lost its balance. The wobble begins slowly. So slowly that you would not notice it for years, perhaps decades. But the mathematics are clear. Computer simulations run by scientists at institutions around the world all reach the same conclusion. Without lunar gravity holding us steady, Earth's axial tilt will eventually wander between extreme values. Some simulations show the tilt dropping toward 0 degrees. Imagine a world with no tilt at all. The sun would hang at the same height in the sky all year round. There would be no summer, thus no winter. The equator would bake under constant direct sunlight. The poles would freeze in permanent twilight. Weather patterns that depend on seasonal temperature differences would collapse. Other simulations show the opposite. The tilt could increase toward 40, 50, or even 80 degrees. Imagine a world tilted so far that the poles point almost directly at the sun for part of the year. 6 months of endless daylight would roast one hemisphere while the other froze in 6 months of endless darkness. Temperatures would swing by hundreds of degrees between seasons. No ecosystem on Earth has evolved to survive such extremes. The truth is that scientists cannot predict exactly what would happen. The behavior of a moonless Earth is not something we have ever observed. We only have models, and models can be wrong, but every model agrees on one thing. Stability would be replaced by chaos. Here is something that makes the situation even more complicated. Earth is not alone in the solar system. Other planets exert gravitational influences on our world. Jupiter, the giant of our cosmic neighborhood, tugs on Earth constantly. So do Venus and Mars. Normally, these tugs are balanced by the Moon's stabilizing presence. Without the Moon, these outside influences would have greater effect. Some scientists believe that Mars provides a warning of what could happen. Mars has no large moon. Its 2 tiny satellites, Phobos and Deimos, are too small to provide meaningful gravitational stabilization. As a result, the Martian axial tilt has varied wildly over its history. Evidence suggests it has swung between 0 and 60 degrees over millions of years. Some researchers believe this instability contributed to the loss of Mars's atmosphere and water. A stable climate requires a stable tilt. Earth could face the same fate. But the changes would not happen overnight. The drift would be gradual, unfolding over thousands and millions of years. Humanity might have time to adapt, or humanity might not survive long enough to see the worst effects. Other disasters, more immediate, would demand our attention first. Still, the slow death of our seasons deserves consideration. Imagine a world where winter in New York lasts 8 months instead of 3. Imagine a summer in Australia that brings temperatures of 60 degrees Celsius. Imagine monsoon patterns in Asia that no longer arrive on schedule, leaving billions without the water they need for farming. Imagine the Amazon rainforest, evolved over millions of years for specific temperature and rainfall patterns, dying as the climate lurches unpredictably from one extreme to another. Agriculture would become nearly impossible. Crops are sensitive to temperature and day length. Wheat, rice, corn, and soybeans all depend on predictable seasons to flower and produce grain. Farmers cannot plant if they do not know when spring will come. They cannot harvest if they do not know when fall will arrive. The global food system, already strained by population growth and climate change, would collapse. Animals would suffer alongside plants. Migration patterns, honed over millions of years, would become useless. Birds that fly south for winter would find that south is no longer warm. Whales that travel to specific breeding grounds would discover those grounds are no longer suitable. Hibernating mammals would wake at the wrong times, finding no food waiting for them. The oceans would change too. Ocean currents are driven partly by temperature differences between the equator and the poles. If the axial tilt changes, these temperature differences would change as well. Currents that have flowed in the same directions for millions of years might slow, shift, or reverse entirely. Marine ecosystems that depend on specific current patterns would be disrupted. There is a strange and unsettling detail that scientists have discovered through studying Earth's past. Our planet's axial tilt has not always been perfectly stable, even with the Moon. It wobbles slightly over a cycle of about 41,000 years. This wobble, combined with changes in Earth's orbit, has helped trigger ice ages throughout history. The Moon has kept this wobble small. Without the Moon, the wobble could become extreme. Some researchers have speculated about even stranger possibilities. If Earth's tilt became very large, the planet might eventually settle into a new stable state, perhaps lying on its side, like Uranus, perhaps with the poles facing the Sun permanently. These scenarios are unlikely, but not impossible. The mathematics allows for many strange outcomes. What is certain is that the Earth we know would cease to exist. The blue marble that astronauts photograph from space, with its recognizable continents and weather patterns, would become something alien. Future generations, if any existed, would inherit a planet their ancestors would not recognize. The maps would be wrong, the calendars would be meaningless, the stories passed down about how the world once was would sound like fairy tales. But those future generations face another threat first, one more immediate, one falling from the sky at this very moment. The bombardment has begun. The sky is falling. This is no longer a metaphor. It is reality. In the weeks and months following the Moon's rupture, Earth becomes a target. The debris cloud that once was our lunar companion has spread across hundreds of thousands of kilometers. Most of this material remains in orbit, circling Earth in chaotic patterns. But gravity is patient. It pulls. It tugs. It drags. One by one, fragments begin their descent. The smallest pieces arrive first. Dust and pebbles, no larger than grains of rice, enter the atmosphere at speeds exceeding 40,000 kilometers per hour. At these velocities, even tiny objects generate tremendous heat. They glow white-hot, streaking across the sky as meteors. On any normal night, you might see a dozen shooting stars. Now, you see thousands. For a brief moment, it is beautiful. The sky dances with light. Children point upward in wonder. Adults pause their panic to appreciate the spectacle. It feels almost magical, like the universe is putting on a show. But the show is just the opening act. Behind the dust come the rocks, fragments the size of footballs, the size of cars, the size of houses. These do not burn up completely. They survive the fiery passage through the atmosphere, trailing smoke and fire before striking the surface with devastating force. A rock the size of a car carries the energy of a small nuclear bomb. When it hits the ground, it does not simply land, it explodes. The kinetic energy converts instantly to heat and pressure. A crater forms, shock waves radiate outward. Anything within a kilometer is destroyed. Now imagine hundreds of these impacts happening every day. Scientists have studied impact events throughout Earth's history. The evidence is written in the rock. Craters dot our planet's surface, though many have been eroded by time or hidden by vegetation. The most famous is the Chicxulub crater in Mexico, formed 66 million years ago when an asteroid 10 kilometers wide struck the Yucatan Peninsula. That impact ended the age of dinosaurs. It killed 75% of all species on Earth. The fragments falling now are smaller than that ancient asteroid, but there are many more of them, and they keep coming. The first major impact might strike an ocean. This would seem fortunate at first. No cities destroyed, no immediate death toll. But an ocean impact creates its own horror. When a large rock strikes water at cosmic speeds, it displaces millions of tons of seawater instantly. A tsunami forms, not a normal tsunami, triggered by an earthquake, rising perhaps 10 or 20 meters high. This tsunami could reach hundreds of meters. The wave would cross the ocean at the speed of a jet airplane. Coastal cities would have hours of warning at most. Evacuation would be impossible. When the wave arrived, it would sweep inland for kilometers, erasing everything in its path. Buildings, roads, bridges, people, all reduced to rubble and carried back out to sea as the water retreated. A single ocean impact could kill tens of millions. But the impacts would not stop with one. The debris field contains countless fragments, and Earth is a large target. Some would strike land. The consequences would depend on where they landed. An impact in an unpopulated region, like the Sahara Desert or the Siberian wilderness, might cause relatively little immediate harm. A crater would form. Dust would rise into the atmosphere, but few lives would be lost directly. The world might count itself lucky. An impact in a populated region would be catastrophic. Imagine a fragment the size of a small building striking downtown Tokyo, or London, or New York City. The explosion would be measured in megatons. Everything within several kilometers would be vaporized. Fires would spread across tens of kilometers. The death toll would reach millions in seconds. And then there is the dust. Every impact throws material into the atmosphere. Small impacts produce local dust clouds that settle within days. But large impacts can inject dust into the stratosphere, where it remains for months or years. This dust blocks sunlight. It cools the planet. It disrupts agriculture. A single large impact can trigger what scientists call an impact winter. Global temperatures drop by several degrees. Growing seasons shorten. Crops fail. Famine follows. Now imagine not one large impact, but dozens, hundreds. Over months and years, the cumulative effect would be devastating. The atmosphere would fill with dust. The sun would become a pale ghost of itself, barely visible through the grey haze. Temperatures would plummet worldwide. Plants would die. Animals would starve. The food chain would collapse from the bottom up. There is historical precedent for this scenario, though on a smaller scale. In 1815, the volcanic eruption of Mount Tambora in Indonesia ejected so much material into the atmosphere that the following year became known as the year without a summer. Crops failed across Europe and North America. Food prices soared. Thousands starved. The lunar bombardment would be far worse than Tambora. It would be worse than any single event in recorded human history. Only the great extinction events of the distant past would compare. Here is a grim detail that scientists have calculated. If just 1% of the moon's mass fell to Earth over a period of several years, it would deliver more energy than all the nuclear weapons ever built. The planet would be reshaped. Continents would be scarred with craters. The atmosphere would be choked with debris, and the impacts would not be evenly distributed. Earth rotates, and the debris cloud moves in complex patterns. Some regions might suffer repeated strikes while others remain relatively untouched. Wars might erupt over access to safe zones. Millions would flee from vulnerable areas, creating refugee crises beyond anything in human experience. Underground shelters would become humanity's only hope. Deep bunkers, stocked with food and water, might protect small populations from the worst effects. But these shelters could not hold everyone. Billions would be left on the surface, exposed to falling rocks and darkening skies. The age of humanity, so proud and confident, would face its greatest test. But even as the rocks fall, another transformation is beginning. The Earth itself is changing. The oceans, the atmosphere, the very climate that has nurtured life for billions of years is shifting into something new and terrible. The bombardment continues. But even as rocks fall from the sky, a slower catastrophe is unfolding. The Earth itself is transforming. The blue planet that has nurtured life for billions of years is becoming something else. Something hostile. Something alien. Let us begin with the oceans. Water covers 70% of our planet's surface. It is the source of all life. It regulates our climate. It feeds billions of people. And now it is rising. Each impact that strikes the ocean transfers enormous energy into the water. This energy becomes heat, not enough to boil the seas, but enough to warm them measurably. A single large impact can raise ocean temperatures by fractions of a degree across entire basins. Dozens of impacts, hundreds of impacts, and the cumulative warming becomes significant. Warmer oceans expand. This is simple physics. When water heats up, its molecules move faster and spread apart. The ocean does not gain more water, but it takes up more space. Sea levels rise. Scientists estimate that a 1-degree increase in average ocean temperature could raise sea levels by several meters over time. The impacts from lunar debris could cause warming far beyond 1 degree. Combined with the melting of polar ice triggered by climate disruption, sea levels could rise by 10 meters, 20 meters, perhaps more. Imagine the coastlines of the world redrawn. Miami underwater, Shanghai drowned, Bangladesh, home to over 160 million people, almost entirely submerged. The great coastal cities that humanity built over centuries would become underwater ruins, monuments to a civilization that trusted the seas to stay where they were. But rising seas are only part of the story. The atmosphere is changing too. Every impact throws dust and debris into the air. We have already discussed how this dust blocks sunlight and cools the planet. But there is another effect, less obvious but equally dangerous. The impacts also release gases. When rock vaporizes upon impact, it releases whatever chemicals it contains. Lunar rock is rich in oxygen, silicon, and various metals. When this material enters the atmosphere, it reacts with existing gases in complex ways. Some reactions produce aerosols that reflect sunlight, adding to the cooling effect. Others produce compounds that could damage the ozone layer. The ozone layer sits high in the stratosphere. It absorbs ultraviolet radiation from the sun, protecting life on the surface from harmful rays. Without the ozone layer, UV radiation would cause widespread skin cancer, blindness, and crop failures. Plants and animals that have evolved under the protection of this invisible shield would suddenly find themselves exposed to dangerous radiation. Scientists are not certain how the lunar bombardment would affect ozone. The chemistry is complex and depends on exactly what materials enter the atmosphere and how they react. But the risk is real. A damaged ozone layer, combined with falling temperatures and rising seas, would create a triple threat to life on Earth. And there is more. The impacts generate fires. Large fragments striking forested areas ignite wildfires that spread across thousands of square kilometers. These fires release massive amounts of carbon dioxide and smoke into the atmosphere. The smoke adds to the darkness already caused by impact dust. The carbon dioxide, once the dust settles, would contribute to long-term warming. This creates a strange and contradictory climate scenario. In the short term, dust and smoke would cool the planet dramatically. An impact winter would grip the world, lasting years or perhaps decades. Temperatures would drop, glaciers would advance, agriculture would fail. But in the long term, once the dust settled, the accumulated carbon dioxide would trigger warming. The planet would swing from extreme cold to extreme heat within a century. Ecosystems that somehow survived the cold would then face deadly heat. Species that adapted to winter conditions would find themselves in a world that was suddenly too hot. This whiplash effect would be devastating for life. Consider the plants. Plants are the foundation of almost every ecosystem on Earth. They convert sunlight into food. They produce the oxygen we breathe. They provide shelter and sustenance for countless animal species. But plants cannot move. When conditions change, animals can migrate. They can seek new habitats. Plants are rooted in place. They must endure whatever conditions arise where they stand. An impact winter would kill plants that need warmth. Tropical forests would die back dramatically. Crops that depend on specific temperature ranges would fail. Only cold-adapted species would survive, and even they would struggle under darkened skies with little sunlight for photosynthesis. Then, when the warming arrived, cold-adapted plants would die too. The species that had survived the winter would find themselves in a world too hot for their biology. There would be no time for evolution to produce new species. The changes would happen too fast. The result would be mass extinction of plant life. And with the plants would go the animals that depend on them. Herbivores would starve. Carnivores that prey on herbivores would starve next. The food web would collapse layer by layer. There is a haunting parallel in Earth's history. 66 million years ago, the asteroid that killed the dinosaurs also triggered climate chaos. First came the impact winter. Darkness and cold lasted for years. Then came warming, as greenhouse gases accumulated. Scientists estimate that 75% of all species went extinct. The lunar bombardment could be even worse. Not a single impact, but hundreds. Not over days, but over years or decades. The planet would have no time to recover between blows. Ocean currents, already disrupted by the loss of tidal rhythms, would shift further as temperature patterns changed. Cold water that should sink at the poles might stay at the surface. Warm water that should circulate toward higher latitudes might stall at the equator. The great conveyor belt that moves heat around the planet would slow or stop entirely. Weather patterns would become unrecognizable. Rain would fall where deserts once stood. Droughts would grip regions that used to be lush. hurricanes feeding on warmer ocean waters might grow to sizes never seen before. The Earth that emerges from this transformation would not be the Earth we know. It would be a wounded world, scarred by fire and flood, or choked by dust and gas. Life would not end entirely. It has survived catastrophes before, but the life that remained would be fundamentally different. And somewhere in this chaos, humanity would fight to survive. In the midst of chaos, life persists. It always has. Through asteroid impacts, volcanic winters, and ice ages, life has found a way to endure. The question now is not whether life will survive, but what kind of life will emerge from this wounded world. Let us consider humanity first. We are a resilient species. We have survived ice ages with nothing but stone tools and fire. We have spread across every continent, adapting to deserts, jungles, mountains, and frozen tundra. We have built civilizations that reach toward the stars. Surely we can survive a broken moon. But survival and thriving are not the same thing. In the immediate aftermath of the lunar rupture, human civilization would face unprecedented challenges. Power grids would fail as debris strikes destroyed infrastructure. Communication networks would collapse. Supply chains that carry food, medicine, and fuel across continents would break down. Within weeks, the modern world would begin to unravel. Cities would become death traps. Millions of people packed into small areas, dependent on constant flows of food and water from distant sources. When those flows stopped, hunger would set in quickly. Clean water would become scarce. Disease would spread through weakened populations. Those who survived the initial chaos would face harder choices. Stay in the cities and hope for rescue that might never come, or flee to rural areas where food might still be grown, assuming the darkened skies allowed anything to grow at all. Scientists have modeled scenarios similar to this. Nuclear winter studies from the Cold War era provide useful data. Following a major nuclear exchange, global temperatures could drop by 10 to 20 degrees Celsius. Agriculture would fail worldwide. Billions would starve within the first year. The lunar catastrophe would produce similar effects, perhaps worse. The bombardment would continue for years, constantly adding new dust to the atmosphere, preventing recovery. The impact winter would not be a single event to endure and overcome. It would be an ongoing assault. Some estimates suggest that 90% of the human population could perish within the first decade. Not from direct impacts, though those would kill millions. Most would die from starvation, disease, and violence as societies collapsed and resources became scarce. But 10% survival still means hundreds of millions of people. These survivors would form the foundation of whatever humanity becomes next. Where would they live? Underground shelters would offer the best protection. Deep bunkers, naturally insulated from surface temperatures and shielded from falling debris, could support small communities for years. Governments have built such shelters, preparing for nuclear war. Some would now serve a different purpose. Caves and mines would also become refuges. Humans lived in caves for hundreds of thousands of years before we built houses. We could do so again. These natural shelters would protect against debris and provide stable temperatures even as the surface world froze. But underground living has limits. Humans need food, and food needs sunlight. The survivors would need to develop new methods of agriculture. Hydroponic systems, growing plants under artificial lights powered by geothermal energy, might provide some food. Fungus farming, raising mushrooms that do not need sunlight, could supplement diets. Insects, rich in protein and easy to raise in confined spaces, might become a staple food. The survivors would also need to venture to the surface eventually. to gather resources, to monitor conditions, to remember what the sky once looked like. These expeditions would be dangerous. Debris would continue to fall unpredictably. Radiation from a damaged ozone layer would pose health risks. The cold would be brutal. A new kind of human might emerge from this crucible, hardened by suffering, resourceful by necessity, deeply aware of how fragile existence truly is. But humanity is not the only life that matters. What about the rest of the living world? The news is grim, but not hopeless. See, mass extinctions have happened before. 5 major extinction events are recorded in the fossil record. The worst, the Permian-Triassic extinction 250 million years ago, killed 96% of all marine species and 70% of land vertebrates. Life nearly ended entirely, yet life recovered. It took millions of years, but new species evolved to fill the empty niches. The dinosaurs rose after the Permian extinction. Mammals rose after the dinosaurs fell. Each catastrophe cleared the stage for new actors. The lunar catastrophe would trigger a 6th mass extinction. Many species would have no chance. Large animals requiring significant food and habitat would die quickly. Specialist species adapted to specific environments would perish when those environments changed. Tropical species, dependent on warmth and stable conditions, would have nowhere to go. But some species would survive. Small animals with low food requirements would fare better than large ones. Rats, mice, and other rodents have survived previous catastrophes. They are adaptable, able to eat almost anything, and reproduce quickly. Insects would also persist. Many species can enter dormant states, surviving months or years without food. Certain plants would endure. Seeds can remain viable for decades, waiting underground for conditions to improve. Some plants can survive freezing temperatures, others can grow in low-light conditions. When the dust finally settled and sunlight returned, these survivors would begin the slow process of rebuilding ecosystems. Ocean life would face unique challenges. Many surface species would die as waters warmed from impacts and surface conditions became chaotic. But deep-sea creatures, living in eternal darkness far below the surface, might barely notice the catastrophe. Hydrothermal vent communities, sustained by chemical energy rather than sunlight, would continue their ancient existence undisturbed. These deep-sea survivors could become the foundation of new marine ecosystems. Just as life may have originated at hydrothermal vents billions of years ago, it could spread outward from them again. There is even a strange possibility that some scientists have considered. The catastrophe might accelerate evolution. Mass extinctions create opportunities. Ecological niches left empty by vanished species become available for colonization. Species that were once marginal can suddenly thrive without competition. In the millions of years following the lunar catastrophe, evolution would produce new forms of life, creatures we cannot imagine, plants with novel adaptations, animals that exploit environments we consider hostile. The tree of life would branch in unexpected directions. This is the strange hope hidden within the horror. Life is tenacious. It finds a way. Even when 99% of species perish, that 1% carries the seeds of everything that follows. The earth would heal. Not quickly, not easily, but eventually. And perhaps, somewhere in that healed world, descendants of those human survivors would look up at a strange new sky and wonder what it was like when the moon was whole. Time passes, it always does. The bombardment slows. The dust begins to settle. The sky, grey and choking for so long, starts to clear. One morning, perhaps decades after the rupture, perhaps centuries, a survivor looks up and sees something remarkable. The sun, pale and weak for so long, shines bright again. This is not the end of the story. It is only the beginning of a new chapter. The question that remains is simple but profound. Can Earth find balance again? Or has the breaking of the moon condemned our planet to eternal chaos? Let us consider what the sky looks like now. The moon, as we knew it, is gone forever. In its place, two large fragments orbit Earth in a complex dance. They are no longer round. Gravity has not yet had time to reshape them into spheres. They appear as irregular masses, tumbling slowly, their broken faces catching sunlight at strange angles. Between and around these fragments, a ring of debris encircles Earth. Not a beautiful ring like Saturn's smooth bands. This ring is messy and uneven, thicker in some places and thinner in others. It glitters faintly at night, a pale reminder of what was lost. Scientists of this future age would study the ring carefully. They would calculate how long it might last. Some debris would slowly fall to Earth over millennia, creating occasional meteor showers. Other material might be swept up by the two large fragments, slowly adding to their mass. The ring would thin and spread over millions of years. Eventually, it might disappear entirely, or it might stabilize into something permanent. Earth could become a ringed planet forever, a strange beauty born from catastrophe. The two main fragments pose a more complex question. Will they remain separate, or will they eventually recombine? Gravity pulls constantly. It never stops. The two fragments exert gravitational attraction on each other, even as they orbit Earth. Over vast stretches of time, this attraction might draw them back together. A slow collision, taking thousands or millions of years, could reform a single body. But this new moon would not be like the old one. It would be misshapen at first, lumpy and uneven, gradually rounding out over billions of years. Its orbit would be different. Its influence on Earth would be changed. Some scientists theorize a different outcome. The two fragments might stabilize in separate orbits, becoming two smaller moons. Earth would have a double moon system, like Mars with its two tiny satellites, but on a much larger scale. These twin moons would rise and set at different times, creating complex patterns of light and shadow across the night sky. The tides, so chaotic in the aftermath of the rupture, would eventually find new rhythms. Not the familiar rhythms of the old moon, but something new. Perhaps a double tide cycle, with one high tide from each fragment. Perhaps something more complex as the two moons tugged in different directions. Ocean life would adapt to these new rhythms over generations. Creatures that survived the initial catastrophe would evolve new behaviors, new breeding cycles, new migrations. The dance between land and sea would continue, just with different music. What about Earth's axial tilt? This remains the great unknown. Without the stabilizing influence of a single large moon, the tilt could wander over millions of years. Seasons could become extreme. Ice ages could come and go with unpredictable frequency. Life would need to remain adaptable, ready to change as conditions shifted. But there is a possibility that offers some hope. If the two lunar fragments remain relatively close to Earth, their combined gravitational influence might provide some stability. Not as much as the original moon, but perhaps enough to prevent the worst extremes. Scientists would need centuries of observation to know for certain. The climate, battered by impacts and choked by dust, would slowly recover. As the atmosphere cleared, temperatures would stabilize. At first, they might swing wildly, lurching from cold to hot as the balance of gases shifted. But over centuries, a new equilibrium would emerge. Rainfall patterns would change. New deserts might form where forests once stood. New forests might grow where deserts once baked. The geography of life would be rewritten across every continent. Humans, if they survived, would adapt. We always have. The descendants of those who sheltered underground would emerge into a transformed world. They would map new coastlines, plant crops in new soils, and build communities suited to new conditions. Their culture would be forever shaped by the catastrophe. Stories of the breaking of the moon would be passed down through generations. Religions might form around the event, seeking meaning in the destruction. Scientists would study the lunar fragments obsessively, determined to understand what happened and ensure it never happened again. And at night, those future humans would look up at a sky their ancestors would not recognize. 2 moons rising instead of 1. A faint ring of debris catching starlight. The constellations unchanged, but everything else different. They would see beauty in this new arrangement, because humans always find beauty, even in the aftermath of disaster. Perhaps they would feel grateful. Grateful to be alive. Grateful that life persisted against impossible odds. Grateful that their ancestors had the courage and determination to survive when everything seemed lost. This is the truth about catastrophe. It destroys, but it also creates. It ends old worlds and gives birth to new ones. The breaking of the moon would be the greatest disaster in human history, but it would also be the beginning of a new chapter in Earth's story. Life would continue, unchanged, humbled, but unbroken. And now, as this journey ends, let us return to the present. Look up tonight. The moon is still there, whole, peaceful, silver light falling on a sleeping world. It has guarded Earth for 4.5 billion years. It has stabilized our seasons, gentled our tides, and watched over every creature that ever lived. It is not just a light in the sky, it is a partner, a protector, a friend. We cannot control the universe. Asteroids wander, rogue planets drift. The cosmos is vast and indifferent to our small concerns. But for now, tonight, the moon remains. Let its light remind you of how precious this moment is. This world, this life, this breath. Close your eyes, feel the pull of gravity holding you gently to the earth. Imagine the moon above, keeping watch as it always has. You are safe, you are home, you are part of something ancient and beautiful. Rest now. Let the silver light fill your dreams.